To welcome everyone for this to this next event in the seminar series on trustworthy, complex, and intelligent series. My name is Olga Fink. I'm assistant professor at ETH Zurich, and the seminar series is jointly organized with the SRADA, but also with North AI, with the NVJL, and with ETH Risk Center. It is my pleasure today to introduce my colleague from ETH, Martin Vechev, who is Associate Professor in Computer Science Department. He will be introducing the concept of certified deep learning to us. And he's not only an excellent researcher, he has also started several startup companies. So possibly he will be also giving us some insights on that. So without further ado, I'm giving the word to Martin. And maybe just for organizational reasons, we will post in the chat a link to a slider where you can post all your questions, but also vote for the questions so that we can also organize the Q&A in a better way afterwards. So please, Martin, the floor is yours.
Okay, thank you very much for the introduction. First of all, can you hear me?
Yes.
Okay, great. So I guess if you guys have questions during the lecture, just go ahead and raise your hand, and I guess Olga can interrupt me. All right. So as Olga mentioned, my name is Martin Vechev. I'm professor at ETH Zurich in the Department of Informatics, and today I'm going to be talking about some of the recent work we've been doing in building trust in deep learning models. All right. So as many of you know, deep learning, which is a form of artificial intelligence, has caused, well, please ask questions here. All right, good. So it's not for me. So deep learning has caused a bunch of disruptions in our society, ranging from autonomous driving, medical diagnosis, natural language understanding, game playing, and many more. So many of these disruptions are based on technical advances over many years, not just over the last 10 years, like things like transfer learning, reinforcement learning, AutoML, and many, many more. So that's very exciting, what's happening in that space, and you constantly get news about progress. Now, well, despite all this progress, right, over many years, there are some key problems that are coming up, that are keep popping up in and keep appearing in this paradigm. And here are some of these issues, right? And you can hear about some of them in more detail in Joshua Bengio's Turing lecture, and of course in many other debates that go on in the community. But roughly speaking, these are some of these points, some of the concerns. Points like we need too much labeled data to learn a good model, a highly accurate model. The models do not tend to generalize well to slight distributional shifts of the data. Like if you have a data set and you maybe change the weather a little bit, the model may start mispredicting. The models generally lack robustness and safety guarantees. They generally lack also background knowledge and knowledge about the world, also reasoning ability about causal relationships, general lack of interpretability, being able to understand the decision, and many other maybe smaller issues, but still important in terms of figuring parameter tweaking and quite unclear when the model works, when it doesn't, and things like this. I'm not going to get into the more applied, let's call it company perspective here to why, deep learning may be actually difficult to use in some settings. For instance, lack of monotonicity. When you're adding more data, being able to guarantee that the accuracy and robustness and whatnot increase. But these are some of the points that are of concern. But so today we're going to be talking a little bit about this point, which is the lack of robustness and safety, and what we can do to build models that are more trustworthy, provably so. And this also tends to, in some ways, touch on some of the other points, like the generalization to similar distributions, and also being able to enforce background knowledge, because enforcing background knowledge comes down to training, which comes down to building models, which some degree is a property, just like robustness and safety. Now, just to give you an example of what goes on here, why this problem is hard. Here is a well-known failure of a deep learning model, which was achieved a couple of years ago in a CVPR paper. So here we have a stop sign, and what the researchers did, they put some stickers on the stop sign, so black and white stickers, as you can see. And so they just then ran the state-of-the-art deep learning machine perception models, and then the models, instead of a stop sign, classify the sign to a 45-mile-per-hour sign. And so, in an autonomous driving setting, this may crash the car, or it may do something bad in this situation. But generally, let's not even think too much from an attacker perspective. Let's just think from a robustness and just how good the model is perspective. That such changes to such perturbations to the input shouldn't really cause the even a small child wouldn't be fooled by these perturbations yet. Yes, state-of-the-art models get fooled. So what we're going to do today, as I mentioned, is we're going to be talking about how to create more safer deep learning models, but also try to keep the accuracy high of the deep learning model, because getting it safer, for some definition of safety, it actually could be possible, but getting it both accurate and safe is actually a very hard problem. It turns out. We'll see why. So you can find more information on this website where we put some of more the latest research and papers and systems that we release. Now, this space of creating certifiably safe and robust models is actually technically quite a rich space. So it's very suitable, I think, for interesting PhD topics and just general interest. There is optimization, of course, going on. There is abstractions, which is symbolic reasoning, convex relaxations, and there's projections, finding the nearest point of the red point onto a surface, and of course logic to some degree. So a lot of these topics, which are really the underlying topics that I think a lot of machine learning will go to, these mixtures of these topics, not just gradient-based optimization or statistical reasoning, and not just logical reasoning, discrete reasoning, but also some combinations of this is, I think, where we'll see a lot of interesting developments in the future. And this topic of creating safe and robust models is just one example of this intersection of these topics here. Now, just to give you a more concrete example here about the kind of properties we would like the model to be safe against. So let's look at robustness, specifically local robustness. Even though the techniques that we discuss are actually fairly general, not just restricted to local robustness. So we have the following situation here. We have a digit 8, we have an image 8, and what we can do to that image, we can do all kinds of perturbations. We can rotate it, flip it, brighten it, add noise like patches, like we saw in the previous example, or we can perhaps even have some generative model that makes maybe takes a face and flips it around. Maybe some other model which can perturb the input. And we have some machine learning model here, some neural network that does classification. And what would like to happen is that these perturbations to the input don't really affect the classification. So all of these perturbations classify to 8. But that's not guarantees in general. That's difficult to achieve. It is possible that some of the perturbations, maybe not many, but some may not classify to 8, maybe classify to 6 or 9 or something else. All right, so we are going to stick to this kind of robustness thinking as far as the talk goes, but the methods are actually quite general. Now, why is the problem hard in terms of ensuring that all the possible perturbations, in this case, classify to the same label? Well, in general, it's impossible to brute force all the perturbations. So if you imagine you have 784 pixels and you have 2 choices per pixel, and in reality it's a lot more, then you'd end up with 2 to the 784 exponential number of images that you need to run for the classifier. At the same time, which is not feasible practically. At the same time, standard solvers like mixed integer linear programming solver or satisfiability modulo theory solvers like SMT solvers that are heavily used in verification do not scale to the kind of non-linearities that these deep learning models have, like different activations like sigmoids, stan H's, combinations of these ReU, different kinds of ReUs, and so on, activation layers. And so we need methods, we need new techniques to be able to prove that no matter how you actually perturb an input or whatever specification is it that you have, the classification actually doesn't change. And so the key technical insight behind a lot of our work in this space, and a lot of the work in general in the field, in the certification and certified training space, comes down to this insight here. So what we were thinking when we started getting into this space is that neural networks, generally deep models, are some kind of numerical programs, some restricted numerical programs. And there's been about 40 years of research on numerical approximations and abstractions that the community has done, the programming languages community, program analysis community, for handling large programs, improving properties. So it's a general paradigm of approximating infinite spaces called abstract interpretation, and specifically a sub-paradigm of abstract interpretation called numerical abstract interpretation. It was invented back in the late 70s by Patrick and Radia Cossot. And so we were thinking, why don't we just, if you like, compile the deep neural network and translate it into a form which can be analyzed by all of these techniques that people have developed over the last however many years. And this was the first work we did, which kind of triggered a lot of, I guess, interest in terms of scaling certification of deep neural networks. And so that was the high-level idea. It was really simple. Take a machine learning model and compile it into a representation to which you can use a lot of these advancements over the last 40 years on numerical reasoning. So let's give the idea about this. So imagine that you have this digit 8 that we showed before, this image. And over here, let me use the marker. By now, I'm used to it from the lectures. So, so we have some digit 8 over here, some image. And what you want to do is you want to put capture the perturbation space that you're interested to make to this image, but potentially from a generative model, potentially from some other perturbation, rotations, and whatnot. But let's use potentially something that can be captured by formula. So over here we see for each pixel x0 to 783, 784 pixels, we can put not a concrete value like 0 or 0.975. We can put some range on the possible values that the pixel can take. So think of it as introducing a little bit of noise to every pixel so that it can change. So this E1 here that you see, this noise symbol epsilon1, is just some symbolic term that ranges between -1 and 1. And the nice thing here is that there could be sharing of symbolic terms between the different pixels. So here they're not shared, E1 to E73, but they could be shared as well in general. Initially, in this particular case, what this captures is an L infinity, or in this case, it's a brightening, but it can capture L infinity perturbations to the input. But it could also be some other formula that captures other possible perturbations to the input, or it could be some model that you abstract that captures rotations or something else. We'll see an example of this later. But this is the high-level idea. So we take this shape, which is described by some formula. So this thing here is described by some formula. And what you do in this setting is and so this could be even a potentially infinite number of points or a large but unbounded number of concrete points that you cannot just enumerate. And what you do is now, instead of just sampling and just running things for the network, you push the symbolic shape for the network. So you push this shape over here for the first layer. And this layer could be an affine layer, could be a ReU layer or something else. And so what it forces you to do is to define the abstract versions of every layer in the network so that it can now process not just concrete points, but it can process a symbolic information, like think of it as some kind of symbolic image here, which captures all the perturbations interesting perturbations to the original image. So you push it through, and once you push it through the first layer, you're going to end up with some shape here, which is represented in the particular abstract domain or convex relaxation shape that you allow, and you push it through, and you push it through all the layers, And all the way at the end, once you finish processing the network, you're going to end up with some shape here, some funny shape, which is also described by some formula. We're not going to read the formula here, but as you can see, there is potentially a relationship between these symbolic terms, which essentially means you can capture relational information, you can capture more complex shapes. And so the problem is there is abstraction going on here, there's relaxation going on here. We are not just, every time we push some symbolic information through the layers, we are actually losing information as well, because the exact effect of this layer on this symbolic shape cannot be captured efficiently into some convex shape. You get a non-convex shape, and you need to abstract that into a convex shape, and your job is to reduce the amount of approximation that you induce. So it's very possible that in your final shape here, there may be just points, these red points that I'm drawing, that actually don't exist really. There is no input point in this hyperbox here, that the hyper rectangle here, that we're looking at, that could generate them. So there is a notion of approximation going on, but the guarantee is that if you're able to prove the property that you care about, then you are successful and you're good. If you are not able to prove the property by using this output shape, then you don't know whether you failed because of approximation, or because it's just the property really doesn't hold. Indeed, there was an image here which got misclassified. Yeah, there is a question. Somebody was talking.
No, I think there was no question.
Okay.
So someone just entered.
No problem. Okay. Anyway, so this is the high-level idea, and think of this as some kind of bound propagation stuff. And the challenging bit here is to define the effect of these layers on the symbolic shape, so that you can propagate them. How do you do this in a way which scales, and how do you do it so that you can handle bigger networks? And how can you do it in a way which doesn't induce approximation loss, to where you're introducing garbage points, false positives into these regions? So that's the high-level idea. And to some degree, even though the paper, this AI2 paper triggered quite a bit of research, it actually didn't invent new ways in which to propagate the symbolic information. It just said, just compile it down to existing languages and just run existing abstractions. And so this begs the question, can you do something better than just treating the neural network as a generic numerical program? And this is how a lot of the research unfolded over the last 3-4 years now. And so what happened was, there's been many relaxations, like the shapes that I'm showing you, that people came up with, which most of them can be summarized in this way, can be called as a single neuron relaxation. And what this means at an abstract level is the following. You are at some layer in your network, and you have a shape here. So this shape over here, this blue shape, is described by some constraints, some symbolic constraints. And in this particular case, this is a zonotop shape, but it doesn't really matter. It is some shape. And now what you want to do is you want to define the effect of the ReLU layer onto this shape. And so in this here, we just have two ReLUs. And so what the single neuron line of research did, it just said, in order to be efficient, what we're going to do, essentially to be able to parallelize stuff on the GPU, we are going to compute the shapes of the formulas of the over here of the output neuron, essentially, as a function only of what goes on in this input neuron here. And the same thing we're going to do for Y2 as a function of the constraints associated with X2. Okay, so we're going to do this. And so essentially what happens here is, so let's just proceed. Essentially, this is going to induce another shape here. Don't worry about the constraints themselves. It's just going to induce another shape, these constraints. But the high level bit here is that the constraints for Y1 depend only on the constraints associated with X1. And so essentially what this means is that you can compute the constraints for Y1 and Y2 in parallel on the GPU, and you can run this in parallel and be done with this. So this paradigm of working, I refer to it as a single neuron thinking, because when you're computing the situation, the constraints for Y1, you do not look at both constraints for X1, X2, you're just looking at the constraints for X1. So this induces some approximation loss. So just to give you an example more concretely, if you are approximating the ReLU, which is in a convex way, with some convex shape, so you have the ReLU function, this is a crossing ReLU because some of the values that X can take, the input neuron, can also be negative, and some of the values can be positive. And so these crossing ReLUs are in fact a significant problem. So that can happen. So the convex shape, if you like, the possible values that the convex shape induces your approximation on X is some range that X can take, and this LX here and LX and UX are just some concretizations that the possible values that X can take is induced by the convex shape associated with that layer where X participates. And so we get some kind of interval concretization here. So X is between LX and UX. And it can be both positive and negative, right? When you consider symbolic shapes. And so what people did, they say, well, what should we do here? We cannot, what should be the value for Y? Y cannot be represented in this way because that's very inefficient. That's not going to work. And that's the whole premise of these approximations. So early on, even there was a paper by Eklers at ATFA 17, which proposed a triangle convex approximation. It says, just represent this triangle here. And this triangle is represented by these three constraints, this one, these three lines, and this one over here. Okay, so do that and then propagate those three lines forward to the next layer. That of course gets quite inefficient for many reasons and doesn't really scale to bigger networks. And so this triggered again quite a bit of different approximations. So for instance, the simple box approximation, which just approximates the ReLU with the this effect with the box. So it introduces a bunch of other points here that cannot actually happen. Over time, there were more clever approximations. So we did some approximation, and in parallel in ICML, there were a bunch of papers also that were looking at other approximations. So this is the zonotop approximation. So it looks like this. So you can capture. So zonotop is just some restriction of convex polyhedra, which is less expensive than convex polyhedra, but it's still more turns out practically more precise than the box. Even though if you look at this example here, and theoretically it's true that the two domains, the two abstractions, are actually non-comparable. One is including points that the other one is not including. Okay, so this one is including this range here, which lacks in the box, and the box is including some values over here, which are lack in it includes these guys over here, which lack in the zonotop deep zone abstraction. There were other abstractions that people came up with over the years, like ourselves and others. So this is the deep poly, again, a restriction of convex polyhedra, another kind of approximation. Okay, maybe there is a question. Okay, so somebody again. Well, there are some questions. Perhaps we can reach Robert from. Okay, let me answer this question after about the enumeration business. Anyway, so there's a bunch of different approximations, and if you actually carefully look at the deep zone approximation, you will see that there's actually potentially an infinite number of non-comparable approximations, because what you can do is you can grow this line to be a little bit lower, and you can grow this line here to be a little bit higher. So you can tilt the whole thing a little bit and just changing the slopes, and then you'll end up with different approximations here. So learning potentially the right approximation also became a thing. But these were just a bunch of different approximations. There are many others. And so this triggered people to write a paper at NeurIPS. There was a paper from Microsoft Research, which justifiably said, well, there are so many different approximations, let's compare them. And they said, well, they stipulated that there is potentially a barrier to a limit to the being able to prove properties about neural networks in terms of these convex approximations. And they essentially say there is a limit. There is a convex relaxation barrier, which essentially is this approximation here, the triangle. So the paper essentially stipulates that triangle is the best thing you can do in terms of convexity, and there's nothing better you can do, and that's about it. So the paper is quite valuable because it looks at different approximations, tries to understand them. But unfortunately, this stipulation that this is the best you can do in terms of triangle is not quite correct. So there is a work we did, and that's why I presented to you in a particular way so that you can see it and think of it this way as well. There is a work we did in slightly after, which showed that by not doing single neuron relaxation, by doing multi-neuron relaxation. So for instance, if you don't just, when you're computing the output for Y1, you don't just look at X1, you can actually look at both X1 and X2. So if you look at your X1, X2 example at the layer, one of the layers, if you look at, there is the relationship between potentially the constraints between an X1, X2 that induces this shape over here. And now what you can do, if you're looking at the single neuron thinking, you would end up with the optimal shape being this one here. Sorry, this one over here, the blue one. This would be the optimal shape. If you do this, if you process the constraints for X1 separately for computing Y1, and then you process the constraints for X2 separately when you're computing Y2. But that's not the best you can do. That's not the best you can do. When you process them together, all these constraints from the previous layer, you can end up with a tighter relaxation result, which is over here, this one over here on bottom. So this KRLU essentially says that don't just think about, what is the abstract effect of a single RLU. Think about, K combination of them. And you can generalize this result to K sigmoid, K tan H, combinations of tan H sigmoid, or combinations of like different activations and so on and so forth. So if you look at, for instance, at something like recurrent neural network, if you find the best convex relaxation for a composition of different functions like tan H and sigmoid, you may be able to get even tighter results. So this space essentially amounts to figuring out what are the best convex relaxations for combinations of activations so that you can balance the scalability and precision. So we implemented a lot of these relaxations and so on in a public framework called ERAN. So this is probably right now the most popular framework for neural network certification. And what it does, it just takes a neural network in some format, like an ONIX format, takes a precondition, like of the kind I showed you, and takes some property you want to prove, like a postcondition, like a robustness, or maybe something else. And internally, it uses a lot of these approximations that I showed you, like this box and zonotope and polyhedra and so on and so forth. There is even faster version of this, specifically implemented on the GPU. You can speed up a lot of these convex approximation relaxations, and combinations with mixed integer linear solvers and so on and so forth. Recently, we have I think this is currently the state of the art result, this Prima, which does multi-neuron relaxations of the one that I just showed you on the previous slide. So all this is implemented, and you can use it to analyze and verify models for different properties. People use it in domains like robotics and image processing and NLP and so on. And this actually won the neural network verification competition last year. There were more than 20 entries from like different universities and labs like DeepMind, Oxford, and Stanford and others. So it won, I think, on 4 out of the 5 categories. On the fifth category, it was tied with another verifier. But we don't really see it so much as a competition here. We're just trying to still understand, what are the limitations, what kind of networks we can certify, what properties we can certify, and so on and so forth. So just to give you an example, just so that you don't think that we are just dealing with noise or L infinity perturbations or things like this, or brightness or patching, we've actually used this framework, and others have used it to verify geometric perturbations. So for instance, if you have the following situation, rotations, for example, of an image by 30 degrees, and you want to, verify that any rotation in some range from 0 to 30 degrees is correct. There is many possible angles here because of interpolation. So it's not just 0, 1, 2, 3, and so on. So you cannot just enumerate this. And so what you typically need to do is you need to take the input, like the input image 3, and then you need to, before you even feed that into the neural network verifier, you need to compute the effect of a rotation function, potentially with different kinds of interpolation, by cubic or bilinear interpolation, on the range from 0 to 30 degrees. And this is going to induce some convex shape, and which captures an over approximations of the possible rotations in that range. And then what you can do is you can then just feed that region to the neural network, standard neural network verifiers. So this, how do you compute like potentially tighter regions, maybe tighter regions than what I'm showing you here, like maybe something smaller that can still be processed by the neural network verifier, is still being quite studied. They can do many more things here than what we did. And of course, you can also do composition of transformations like rotations, followed by translation, followed by noise, followed by patching, followed by whatnot. This, of course, brings up another question of robustness, which is, could you actually synthesize this transformation? Because they essentially become like their own program once you start having compositions of them, find a sequence of transformations that what is the largest sequence, and that you can actually certify. But so that's just an example of using the verification framework. So it's fairly compositional. And I think this way of using certification is going to be more common because what is happening is that you have these methods for verifying networks that are taking some input shape into account, but you have typically a lot of pre-processing of the input, like here in the geometric pre-processing. You can rotate it. You can have sound audio pre-processing, some frequency transform. You could have a generative model, which does some interpolation or does something else. So it's not just taking an image and putting some noise around it and feeding it to the verifier. You may have an entire pre-processing pipeline before that you need to take care of. And that's where also these convex approximations are useful to approximate the effect of the pipeline. So let me give you some thoughts on neural network verification. In my experience, at least, are just some thoughts. One of the problems that we're having, the whole deep learning thing, I think, is this question of specification. What is it that you actually want to verify? And rightfully so, some people may say, look, I mean, this L infinity perturbations, this noise, may not be something that can happen in practice. So why should I care about this, right? And that's a valid concern. And this L infinity business that has been the benchmark for many verifiers, I think it's actually very good for establishing a common specification, not necessarily a useful specification, but it's a common specification, practically useful, but it's a common specification in terms of having something common to improve the methods on. But recently, we were looking at geometric perturbations, generative models, audio processing, and there are many, many more, like NLP pre-processing and so on and so forth. But this question of the specification remains rather open. I think we're still trying to figure out what is a valid specification. In terms of abstractions and relaxation that we looked at these single neuron abstractions, like approximations of this triangle. But the time is coming to, I think, now to look at more complex combinations involving mixed integer linear solvers, involving sampling, involving multiple activations at the same time, potentially looking at non-convexity and non-linear domains relaxations. That's something that only now is starting to get explored. In terms of different network kinds, different network types, most of the work so far has been on classification, a little bit on regression. We need much more on generative models, many different tasks, like in NLP processing. I don't know how many of you are familiar, for instance, with the ACL checklist, which was best paper at ACL 2020, just specifies the kind of perturbations that you want to care about in NLP, natural language processing, but certifying models against those perturbations has not been done yet. And so now the interesting bit here, when you look at different network types, somebody can say, well, I just plug in different network type and it just works. Well, the answer is it doesn't work, because the different network types come up with different activations, combinations, how they're structured. And if you want to get a scalable verifier, you need to tailor it to those combinations. So for instance, when we started looking at recurrent network, we needed to design specific these convex relaxations effects on the particular relaxations and particular activations that I use there. And the properties are different, like in intersection over union or other properties that you may care about, not just pure classification. In terms of network sizes, this is a classic question that always comes up. scalability of verification is improving drastically over the last 2 years, but it still mostly works for small to medium networks, okay? The problem is, there's a fundamental problem here with these methods, is that the deeper the network is, the more precision loss you induce, the more garbage points you introduce by the relaxation. So if you want to scale certification further, and we do want to do that, you want to consider much deeper interactions with training. If you just train the network separately from certification, then you're trying to certify, this would be quite limited, okay? And so what you want is to have new certified training schemes that are more verification aware. And so these training advances in certification will certainly help verification, and also in terms of network compression. Making smaller networks that have more or less the same accuracy would also help certification, because there would be less units to process, and the less units there are, the less approximation is induced. So this is what I wanted to tell you about certification. So now I want to tell you how to use these relaxations that people use for certification to actually come up with training procedures that can produce more verifiable networks. Because if the network is not trained to be verifiable, if you're just training in the standard way, you're not going to be able to verify much, because it's just not trained to be verifiable. And so let me give you the high-level idea about one of the works. Again, this is kind of like AI2 in the sense that it started kind of many people looking at this way. So this is a work we did in 2018 at ICML. And so the idea is actually very simple. The idea says, how do you actually use convex relaxations for training? And what it says is like, so let's just look at it a bit more mathematically. So what it says, look, well, let's take the same setup just like before. Take our region, push it through, get an output shape over here, and let's call this shape to be, this funny symbol here. So S of x is our input, S of x is the region around our input, and M sharp of S of x is the processing of the symbolic S of x region for the model M for the layers, and M sharp just denotes the abstract effects. And so what this thing says, it says, look, why don't you do the following? Push this shape through, and then, let's look a little bit at the math here. And then what it says is, why don't you go and find a point here, find a point inside this region here, which maximizes the loss. Find the point which maximizes the loss. Okay, so that's what this thing says here. And then says, well, and then go find parameters theta, which minimize this, maximization of the loss. So you have this min-max objective here. So you're trying to minimize this parameters theta here, such that you can think of it intuitively. I want to find such parameters here, such values for the parameters, so that it induces a smaller region here. Smaller region, which hopefully makes the loss smaller. And so this is the whole idea about differentiable abstract interpretation. The unfortunate thing here is that you need to differentiate through the code of the functions, the convex relaxation, the functions that compute these convex relaxations, not just through the concrete activations like we normally have. And this code which computes the convex relaxations is actually not so simple. You can still do it, but the optimization problem gets quite complex. You can state it like this on the right, but it can get quite complex to solve the optimization problem properly. But this is the high level idea. So essentially, you differentiate for the layers which compute the convex relaxations in order to find parameters which minimize the loss that is induced by the output shape. So you try to make the shape smaller, if you like. And over time, this was picked up by DeepMind, for instance, and they improved on it quite a bit by changing the loss function here, make it back to a cross entropy loss, and they used the particular abstract domain here, particular relaxation. They only used box, very simple convex relaxation. Our original paper had more convex relaxations. We also improved it later, and there was various improvements to that scheme. And this general scheme is still in use very heavily today. In fact, almost all certified training schemes basically use this scheme that I'm showing you here, this optimization problem, more or less by just varying the kind of relaxations that you're using here in the middle and various tricks like annealing the input, starting with smaller S of X and then gradually growing it and things like this. All right. Now, what happens though experimentally here is not so great. If you look at something like CIFAR-10, which is one of the standard data sets which people compare these methods, 10 means 10 labels. And you look at this L infinity perturbation, which is fairly small, so 2 out of 255. So each pixel is perturbed by 2 out of 255 range. The best network that you can get is about 70% accuracy, and it's about 53.9% certified robustness. So what this means, accuracy is just standard accuracy. Certified robustness just means all of the points which are classified correctly, which are also provably classified correctly in that region. So the point has to be classified correctly, and it also has to be provable using the whatever method it is that you're using to prove that you cannot perturb the point. Okay. The problem is these numbers are low. These are very low numbers. The accuracy, standard accuracy for CIFAR is like in the 99% range. So this 70% business here, even after applying all this certified training, is still low. Of course, certified robustness increases a lot, because without this training, you'd get like 0% or 1 or 2%, very low. But still, this accuracy business is really serious. Nobody's going to use a network which has 70% accuracy when the baseline has 99%, even if it's much more probably robust. And so what ends up here happening is it's a little bit unfortunate, is that what it turns out is that better abstractions, better relaxations do not really help get better results, which is a very strange thing. So you cannot beat the box relaxation. And better engineering didn't really help. So this is very strange, right? And so you need more conceptual advances. So one of these conceptual advances comes from answering this question. So there's a couple of questions you need to answer before you tweak all these GPUs and all that stuff, and hope that something better gets produced by the GPU optimization and so on. And so the first fundamental question is, well, is there a network actually with a perfect accuracy such that when you analyze it with the box, which is the simplest convex relaxation, is exact, so that you can prove the property of interest? So you can think of an analogous question here where you have universal approximation theorems, which says whether the network can approximate at a high level some function precisely. The question is there a network which can, again, approximate this function, but also that the network is provable? So there is additional property associated with the network with a particular convex relaxation. Because if the answer is no, well, why are we even looking at this problem? Now, it turns out that the answer is yes here, that you can do a universal approximation with the certified network. So essentially, there is hope that you can get both certification and high accuracy. This work we did in ICLR 20, one of the students who actually joined us from ETH Physics, more mathematical paper, essentially shows a construction where that's possible. Of course, the construction is not very practical still, and people are trying to improve on it, but at least shows some kind of existence questions. The second question is, which is more annoying, is why are better relaxations, like something better than box, something like Zonotope or polyhedra, are not producing in practice networks with higher accuracy, more certifiability than just simple box when you do certified training? That's very unintuitive thing from a program analysis perspective. And there is a hypothesis here, which is that more complex abstractions, these relaxations, actually lead to more difficult optimization problems. And the reason why this may be the case is because when you have a relatively small number of weights in those parameters of the network, you need to find such parameters which control complex abstractions like this Zonotope and polyhedra, whatever abstractions, which themselves are described by many more parameters. They capture some complicated high-dimensional shapes. And this is quite tricky, and it's quite unlike normal training. And so we hypothesized the situation, and we actually did some work recently, that's from last month, where we actually proved various properties like continuity and smoothness and so on and so forth on the resulting optimization problem, which tend to explain why certain relaxations tends to induce more complex optimization problems, and which makes training harder. So this space is quite interesting to come up with relaxations which actually generate good optimization problems. More constructively, what we did is we came up with a new training method that produces a much simpler optimization problem than the one I showed you before. And so that was an oral paper in ICLR. So it's a work we did with Mislav Balunovic, one of the PhD students in the group. And the method is like remarkably simple. So what it does is again, there's the shape that we always talk about, this shape. And what it does is, let's say that you push this shape for the network for the hidden layer 1 once, and you end up with the following shape over here. And what it says is, rather than keep pushing this shape through, don't push this shape through like before and try to find points that make the loss behave badly, because then you have to differentiate from the code of these convex relaxation computations, which are very complex and optimization problems are hard. So do this instead. Just push it once. Let's push it once through. And what you do now is you do some, base standard adversarial training in the middle of the network. So you take this shape here that we have, and you pick a point inside that shape. So you find a point inside that shape, and using standard optimization. And then what you do is you say, look, let me find a point inside that shape that when I run this point through, I run this concrete point through, I push it through here, push it for H2, for H3, and I end up with a point like X3, okay? And I'm trying to find a point inside the region S1, which when I run from my deep learning network for the layers H2 and H3 that remain, I'm going to end up with some loss function, and I'm on this point X3 and the true label associated with the original point. And then my goal is to find such a point which maximizes the loss. This is just the standard adversarial training. All you're doing is you're doing standard adversarial training in the middle of the network. And so your objective is you're essentially saying, let me minimize the damage downstream. So I'm going to find a point which induces high loss. And then what I'm going to do, you're only allowed to change the network, the layers H2 and H3, so that you minimize the effect of that point on when you push it for H2 and H3. And so that's how it does. It does standard adversarial training for the network instead of normal adversarial training. You just do it in the beginning of the network on the shape. While if you look at what we did before with the other certified training, we were doing it only at the end. And what this thing does is now, look, just do it in the beginning. And here you don't care about optimizing for the code of the convex relaxation, because you are optimizing for these layers H2 and H3 just in the concrete, not in this abstract way. So just mitigate the effect of H2, H3 on the bad point here. And once you're done mitigating, you push that through again symbolically, you go to the next shape, and you do the same thing for the next downstream layer H3. So that's all this did, this code. That's why it's called certified layer-wise training. So that was the idea, and there are many nice problems mathematically here. One of them, which we didn't get to talk about, is projection, because what you need to do is you need to find points inside the shape or on the surface here, not points outside the region, because that doesn't do the job for us. And how do you then project efficiently onto these convex shapes? This is actually not so clear. You can project onto a box in a constant time, or in a general hyperrectangle into the dimension of the hyperrectangle, but you have something like convex polyhedra or restricted convex polyhedra. You don't want to be calling like quadratic programming in the middle of the gradient descent here, because you will not emerge here. And so this problem of how do different restrictions of convex polyhedra affect the projection, that to my knowledge has not been studied in depth, and it's a problem that comes up here a lot, something we're looking at. So anyway, if you do this kind of training, you can get much better results than before, or not say that much better, but still quite a bit better without too much tweaking or doing whatever hyperparameter optimizations. But we get to 78.8 with some tweaks. You can get to maybe 80 plus, but still not close to the 99 range. So we're still not there. We're still not there. So before I wrap up, I wanted to tell you about So I told you a bit about certification and how to use certification during training in these two optimization procedures so that you can build more certifiable networks. But if you look at like code or the other optimization, certified training or the certification in general, what you see is that the networks that you can certify are still not so large. You know, maybe you get to 100,000 parameters, maybe 500,000, but nowhere near the whatever tens of millions of parameters. And so the question is, how can you enhance, how can you benefit from certification on a standard big network like large scale ImageNet network or some other one that you can get at least some certifiability out of this thing? Because if you do end-to-end certified training or code or whatnot, you're going to perturb this huge network, and God knows what happens to your accuracy, and your accuracy will go down, and then, you know. So can you just treat these things compositionally so you don't perturb like standard training in these ways? And so what we did is this work, which I think to some degree would have to be the way that we can benefit from certification. We're talking about large-scale machine learning, because otherwise it's too invasive. So what you want to do is you want to say, look, I mean, I have all these training, certification methods, all that. Okay, abstract them away here into a separate network, put it there. This H theta B, put it there. So whatever advances exist there, code or whatnot, or deep zone or whatever, just keep it there. And then on the other side, just take your standard high accurate training on many GPUs or whatever people do, get these large scale networks, this H theta T, separate, completely separate. And now just come up with a selector here, this H theta S, which decides which, when a sample comes in, X, which of the two networks should it use? Should it use the highly accurate deep network, which is not really too much certifiable, or should you use this small certified network? So kind of trying to predict whether the sample that's coming in would be robust or not. And so what can happen here, what ends up happening here is that it enables you to handle, first time quite large networks over here without killing the accuracy too much. So this has never been done before. If you look at here, you get like, ImageNet, still a little bit restricted to 200 labels. The normal ImageNet, I think, is 1,000 labels. So this ACE architecture says, look, you can actually get to like 70% accuracy, which is quite good. And it's still low. You still get low certified robustness, like 3%, which is low. But still, I mean, first time you can actually get some reasonable accuracy out of this and get some certifiability on pretty large network, which was not possible before. So this compositional thinking is something that we're actually trying to get to. And if you remember the CIFAR results, which I showed you before, right? So you end up, this is like, it was the state of the art, like 78%, 60% certifiability. But now with ACE, you may get something like 91% accuracy of the network and 22% certifiability. So it's non-comparable to this one here. It's non-comparable, it's not strictly better, but at least you're able to get some certifiability out of this, now getting closer to the high accuracy situation. So that's what we think is, if you want to go down to like deterministic certification, this would be like one way to go, but potentially there may be others. Okay, so before I wrap up, just one slide here. So we're actually teaching there's a course at ETH, which is called Reliable Interpretable AI. I think it's Reliable and Trustworthy AI now, which we have taught over the last 4 years. So there we talk about a lot of these techniques in much more detail, also about fairness. So it tries to balance both fundamental techniques from like latest applications. It's attended quite widely at ETH, and we actually made the course public, including all the lectures on YouTube, just last year in the fall. So it's actually publicly available course. Okay, so I hope you enjoyed the lecture, and there is some you got something out of this. Yeah, so I'm happy to take questions. Thank you very much.
Thank you very much.